Alright, hi everyone, my name is Anton and today I'm going to talk to you about structures and algorithms in hyperbolic random graphs. This is the title of my dissertation, which I've been writing over the past 4 years. And yeah, so before we jump right into it, I want to give you a little bit of context. What is this all about? So in computer science, we have this kind of discrepancy where in theory we prove algorithmic problems to be really hard in some cases, but in practice oftentimes these algorithms can still be actually solved quite efficiently. And there are a number of ways to actually bridge this gap and achieve sensible theoretical analysis of these algorithms. And one of these ways is, for instance, to not analyze our algorithms in the worst case, but to just say, all right, you know what? I'm fine if my algorithm performs very good on average, and the worst case may be as bad as it wants to be. So for this, you usually assume a random distribution of your inputs, such that you can actually do an average case analysis. Now, of course, this approach is only as practical as the underlying distribution you're actually assuming to your problem. Now, in the case of graphs, during the past 20 years, it has actually been discovered that many real-world networks, massive real-world networks, do share very similar properties. And I'm talking here about social networks, internet graphs, electricity networks, biological networks, and so on. And the surprising thing is that they all look alike. However, they do look quite differently from the most popular random graph model, which is the Erdős-Renyi random graphs. So, what are these properties that these real-world graphs share? Well, arguably one of the most important things they have in common is a power law degree distribution. So what does that mean? It essentially means that these networks have many nodes of very small degree and very few nodes of an extremely large degree. And if you plot the degree on the x-axis against the number of nodes that have this degree on the y-axis, you will get a function that is proportional to k to the minus beta, where k is a degree and beta is a constant that's intrinsic to the network. So while this is usually agreed upon property of these massive real-world graphs, they do share some other properties that pop up essentially in all other graphs as well. For instance, these graphs typically have a very small average distance. For example, in the real-world friendship network, it is essentially said that you know everybody else on this planet over at most 10 to 15 friend-of-a-friend relations. And if you think about it, 10 to 15 is an extremely small number compared to the 7 billion we actually have on this planet. And this actually holds true for other networks like the internet graph as well. Now, another very important property is the so-called community structures, meaning that, for instance, if I know person A and I know person B, it is extremely likely for person A and B to also know each other. Moving on, most of the nodes in such a massive real-world graph are typically in the same giant component. So usually a constant fraction of all nodes belong to the same connected component in such a real-world graph. And such real-world graphs have typically hub nodes, as we've mentioned before. These are nodes that they are extremely well interconnected with the rest of the graph, and for instance, in the case of the internet, route most of the traffic. Now, if you were to design a random graph model that encapsulates all of these properties, you want to have one additional thing, and that is namely that the random graph model is as natural as possible. Because typically it is, what you can do is you can just more or less in a brute force manner enforce all of these properties, but then you're essentially none the wiser because, yeah, the only thing that tells you are these properties that you already have known about, and you don't learn anything new about the structure of real-world graphs. Now, many many scale-free network models have been proposed, but what we will be focusing on here are the hyperbolic random graphs. And this is essentially the only model that can convincingly explain why both power law degree distribution and community structures occur. Now, hyperbolic random graphs have been introduced in some other work. It is not my own work, but my work focuses on the analysis of these graphs, which is why I will give you a brief introduction to them right now. And to understand hyperbolic random graphs, we have to understand one important property of the hyperbolic geometry. And this important property is that space in the hyperbolic geometry expands exponentially. What does that mean? That means if you draw, for instance, a circle in the hyperbolic plane of 2 dimensions, then the circle will have an area that increases exponentially with the radius of the circle. Now this stands in stark contrast to circles in the Euclidean plane. As you may recall, they have an area which is proportional to r squared. So we have much more space in the hyperbolic plane. And the interesting thing is now, what happens if we draw a hyperbolic circle and distribute endpoints in it uniformly at random? Well, essentially it's very simple. So let's say we have this circle. Then, as I said, space expands exponentially, which means most of the space will be very close to the boundary of the circle. And most points, let's say half of the points, will fall into a ring of constant thickness. Now, a quarter of the points will fall into the next ring of constant thickness, and so on, until you reach the circle with radius r half, and by that time, only a constant number of nodes remain that fall into the last circle. And how does this actually look like when you really distribute points uniformly at random? It looks something like this. And as I said, most of the nodes are very close to the boundary, and just very few nodes are in the center of the graph. And actually, to obtain a hyperbolic random graph, we are almost finished now, because the only thing that remains is to connect 2 nodes if they have distance at most r from each other. Now, distances in the hyperbolic plane are quite complicated to express, so I'll just show you a picture instead. So what you can see here is essentially 2 circles of radius r around the corresponding nodes in the center. And what you can see immediately is that, for instance, the node within the green circle, that doesn't really look like a circle because we have a Euclidean projection of the hyperbolic plane, of course. The node in the green circle has actually many neighbors in this graph because it is so central to the graph, while the node in the red circle has just very few neighbors. And just like that, from the underlying hyperbolic geometry, you essentially get the power law degree distribution, because as you may remember, power law degree distribution says you have many nodes with small degree. These are the nodes that are very close to the boundary, and just very few nodes with very large degree. These are the nodes that are close to the center. And if you do the math, it turns out these graphs do have a power law degree distribution. And similarly, you also get community structures from this random graph model, because if I have A and B as my neighbors, this essentially means that they are very close to me in the hyperbolic plane. And then this means is that they are also quite likely to be very close to each other. So this model turns out to be actually quite elegant, quite natural. But not only is it nice for theoretical analysis, it has actually also been proven to be quite applicable to real-world problems. For instance, what some other authors did is they took the internet graph and embedded it into the hyperbolic plane such that it looks like a hyperbolic random graph. I will tell you how this works a bit later. But the nice thing that they achieved with this embedding was they had an extremely successful greedy routing. How does this work? Assume I am a node in the internet graph, and now I get a packet that I have to route. And contained in this packet is the hyperbolic coordinates of the destination of the packet, and I know the hyperbolic coordinates of all my neighbors. Now what I can do is, I can simply send the packet to my neighbor that is closest in the hyperbolic space to the destination of the packet. This is just a very simple greedy routing protocol, but the embedding was actually so good that they achieved a 97% success ratio of the greedy embedding, which is extremely surprising because if you do the same thing in the Euclidean plane instead of the hyperbolic plane, you just get a 14% success ratio, much worse. And the paths of the greedy routing were just 10% longer on average than the optimal path. Now, this result actually inspired me to work on these graphs because I find this very amazing that this is a very clean mathematical model, but still has very crisp applications in the real world. But at the time that we have studied these graphs, basically just very few properties were known. So what we did is, in our thesis, we contributed 3 main chapters essentially that have all been published in conferences, in computer science conferences. And I'm going to talk to you just briefly about each of these chapters. Unfortunately, we don't have enough time to go into the details of all the results that we have, but I will give you one exemplary statement excerpt from every chapter. First of all, we're going to talk about cliques in the hyperbolic random graphs, which are complete subgraphs, of course. Then we have the diameter, which is the longest, shortest path in the graph. And then we're going to talk a little bit about embeddings of real-world graphs into the hyperbolic plane. So let's jump right into it. First of all, we asked ourselves, well, how many cliques are there in the hyperbolic random graph? And cliques are, of course, a very fundamental problem in computer science because, for once, it is a very, very simple structure. But on the other hand, it is a very good notion of a community in a graph, and it's also more or less a generalization of clustering in these graphs. And typically, finding cliques is also very hard on general graphs, which makes the problem very interesting. So again, we have a lot of results here. Let me just show you one of them. We obtained a lower bound on the number of nodes in the clique in the hyperbolic random graph. And the proof was actually quite simple. So what we did is, we have the hyperbolic circle that contains the graph. And we subdivide the circles into equally sized circle sectors. And we do this in such a way, we choose the angles in such a way that every circle sector has a geometric diameter of at most r. Now if you recall, 2 nodes are connected when the distance is at most r, which immediately means that every such circle sector is actually a clique. And this is essentially all that you have to do. Now the only thing you have to do is, analytically, you find the sector with the largest amount of nodes, and then you're essentially done. You have found the number of nodes in the clique. Now we have more results in this chapter. You can look at it in the thesis if you want to. What we found is that essentially the clique number, so the size of the largest clique in the graph, behaves as in other random graph models, except when the power law exponent becomes 3 or larger, which does occur in real-world graphs. And in that case, the hyperbolic random graphs still have a diverging clique number, which means it increases with n, while all other models predict simply 3, which is extremely unrealistic and does not happen in real-world graph. So the predictions of the hyperbolic random graphs are actually much closer to real-world examples of these graphs. Moving on, in the second chapter we talk about the diameter of the hyperbolic random graphs, and diameter is also a very fundamental structure. It is essentially the longest, shortest path in the graph. And when we talk about shortest paths here, we of course mean hop distances. So we are not concerned with hyperbolic distances in the shortest path, but just with hop distances. For instance, in this graph, I think the longest shortest path is of size about 13 or something, 13 hops. Now, again, we have a lot of results here. Let me just show you one exemplary proof. So we have shown when the power law exponent is between 2 and 3, we have analyzed the diameter. How did we do that? Well, first of all, we observed that the nodes in the center, so in the circle of radius r12, they form a clique. This is essentially the same observation as we had before. Then we computed an inner band, and this inner band contains all nodes that have a monotone path to the center, meaning that if I'm a node in the inner band, I will have a neighbor that is closest to the center than I am. And even though it doesn't look like this in this picture, usually when n gets big enough, the inner band covers almost the entire disk, and the outer band is just of thickness log n, or log r. And then you can easily show that the diameter of the nodes in the inner band is just log n, so extremely small. So all that remains is you have to look at what happens in the outer band of the hyperbolic random graph. Now here we have a very simple approach. We do the following. First of all, we find the largest circle sector such that there is no node in the inner band in this circle sector. And in this example picture, for instance, this is the circle sector we're looking for. So if you have a look, this sector contains no node in the inner band. Now what you do next is you say, all right, let's count. Oh yeah, so you can just simply compute the angle of the sector analytically. And then what you do is you count the number of nodes in this circle sector that are in the outer band. This essentially amounts to just multiplying the angle by n. So you get some polylogarithm. And then you can do a very simple observation, which is that, okay, if you have the longest shortest path, it can use at most all of these nodes in the sector before it reaches a node in the inner band. And once you have a node in the inner band, you can reach the center very quickly, and all other nodes as well. So it turns actually out that the size of the circle sector dominates the length of the longest shortest path, and you have an upper bound on your diameter. And while this proof is essentially very simple, it's still improved upon a previous result that existed in the literature that had a much more complicated proof and whose upper bound in the diameter was much, much larger than ours. All right, so moving on, let us come to the last main chapter of my thesis, which talks about efficient hyperbolic embeddings. And for me personally, this was the most exciting topic. I will explain to you why in a second. So this is why I want to spend a little bit more time here on this topic to actually tell you a little bit about it. And as we have found out, this is also the topic that excites actually most other authors. So we have received multiple requests for our code, and we actually already have a few citations, even though this paper was only released in 2016. All right, so what is this all about? Well, as you may remember, I was talking about in the introduction, I was talking about the internet embedding into a hyperbolic plane. And as I said, this result I've personally found very exciting. And when I read about this result, I was very eager to try it on different graphs. I wanted to find out, well, what else can we do with it, right? You have this very good greedy routing, but are there other things you can achieve, and are there other graphs you can embed? So we wanted to try out this algorithm, and what we very quickly found out, and what the authors of this paper, which actually appeared in Nature, a very known journal, so what the authors of this paper admitted themselves in a follow-up paper is the embedding of the internet graph required substantial manual intervention and does not scale to large networks. And this was, of course, very tragic to us, because we were not able to apply this algorithm to different graphs, essentially. And what's even worse is that the runtime of the algorithm was n squared, and n squared is simply too slow on real-world instances, because we are usually talking about instances with millions of nodes, and even if you have a large computing cluster at your disposal, n squared in this case is just too big. So we asked ourselves, well, can we do better? Can we find an embedding algorithm that is actually efficient while still maintain a high quality of the embedding? And before I can show you our embedding, let me just briefly tell you what previous embeddings did, so that I can show you what we did differently to achieve better results. So just a very rough introduction. What do you actually want to do when you get to obtain such an embedding? Your input is a graph, just a graph structure of nodes and edges. And what you want to do is, if two nodes are connected, you want to place them nearby in the embedding, so in the hyperbolic plane. And if two nodes are disconnected, you want to place them far apart in the hyperbolic plane. Now, this essentially amounts to, for every node, you have to find a radial coordinate and an angular coordinate. As you may recall, actually the radial coordinate of a node depends in the hyperbolic random graph model how many neighbors they have. So if you go the other way, if you get a graph and want to have the hyperbolic coordinates, you can essentially just look at the number of neighbors a node has, and from there on almost immediately infer the radial coordinate of this node. So radial coordinates are easy. The hard part of the embedding is actually finding the angular coordinates of the node. So for the rest of the talk, we will concentrate on finding angular coordinates. So how does this work in classical approaches? So assume we start with an initial embedding of high degree nodes, however you want to obtain it. You can have a look at my thesis for more details. Assume we have this initial embedding. And then we just subsequently add more and more layers of nodes to the embedding. And how you add such a layer is for every node in the layer, you scan the whole angular range at the resolution 2 pi over n. So essentially you look at endpoints, and at every point you evaluate the fitness of the node if it were at this position. And in the end, you just move the node you're currently looking at to the position with the best fitness. Very straightforward. Now, how do you evaluate the fitness at a certain position? This works with the edge likelihood. Now, what I didn't tell you so far is that hyperbolic random graphs actually have a generalization where you not only connect two nodes if they are close together, but you can actually provide a probability for an edge being there between two nodes, and this probability depends on the distance between two nodes. Now, the formula is not really important. The important thing is that you understand that this probability function is essentially just a smooth step function. Okay, and t is a parameter of this probability function, which essentially allows you to adjust for how strongly you want to penalize edges that are too long and non-edges that are too short. So you can use this edge likelihood for graph generation, but you can also use this for likelihood computation, for the fitness computation, because what you can do now is for every node, you can just essentially sum over all its neighbors at the logarithm of this probability, and then you sum over all non-neighbors and add the logarithm of 1 minus the probability, and this gives you the fitness of a node. And the larger the fitness, the better the position for node is. And that's essentially the overall algorithm that previous authors used. What's the overall runtime? Well, you have to embed all nodes. For every node, you have to scan the whole angular resolution, the whole angular range at resolution 2 pi over n. So you scan at n points, which is another factor of n. And in the end, you compute the log likelihood, where you have to sum overall neighbors and overall non-neighbors, which is again a factor of n. So this gives you a total runtime of n cubed, which is even worse than we have seen before. So how did we improve on that? Well, obviously we have to embed all nodes. There is no way around that. But we can do something smarter than scanning at resolution 2 pi over n, and we compute the log likelihood way faster. So how does that work? So what we observe is that typically a node is placed very close to its already embedded neighbors when it arrives to the graph. What this means is we can just compute a weighted average position of the pre-existing neighbors, sample a few points around this average, and then use the point with the best log likelihood. In our experiments, it turned out that this was actually good enough to find a very well-suited position. Now, how do you compute the log likelihood faster? Again, we made this very simple observation, which is the log likelihood consists of two parts. The first part is actually fine because you sum over all neighbors, and the number of neighbors, meaning that the number of edges in such a graph, is typically of the same order as the number of nodes. So this one is actually fine. The problem is the second part where you sum over all non-neighbors, which is as large as the entire graph almost. So we have to improve this part, but again we can make a very simple observation, which is that if two nodes are far apart, then PUV goes to 0. If they are nearby, then PUV goes to 1. But if PUV goes to 0, then the logarithm of 1 minus PUV is essentially 0. So these nodes do not contribute to our log likelihood. So it actually suffices to consider close nodes that are not connected to us. And again, if you didn't do any huge mistakes in your embedding, this means that when you embed a node, the number of other nodes that are geometrically close to you is actually, again, constant on average. And yeah, that's essentially it. So how does such an embedding look like once you have finished? It may look something like this. And you can compare this to the original graph, which was generated with the hyperbolic random graph model. When you compare these two graphs, you can actually see that they look more or less the same, with small shifts. But it's essentially the overall structure of the embedding is the same. So this is pretty good. And our algorithm runs in n times polylog of n, so it's extremely efficient. In fact, it's so efficient that we were the first that were able to run large-scale experiments on our algorithm. And this wasn't possible before. Our previous embedding algorithm papers usually had only 1 or 2 graphs they tried their embedding on. But since we had such an efficient algorithm, we could do more. So what we did was the following. We chose, for all parameter combinations, the power law exponent between 2.1 and 2.9, t, which is just essentially the noise in the graph between 0.1 and 0.9, the average degree between 2 and 32, the number of nodes between 500 and 128,000. For every such parameter combination, we sampled 10 different hyperbolic random graphs, and this amounts to 6,250 graphs. And for every of these graphs, we wanted to ask ourselves, how good is the embedding? And usually what you do to figure out the quality of the embedding is this, you look at the so-called 5-high plot, which plots the original angle against the inferred angle. Now, as you may recall, finding out the angles of the nodes is actually the hard part. So when this plot resembles more or less a straight line, you're actually fine. But again, we have 6,000 graphs, so we can't look at 6,000 plots. So what we need to do is we need to boil down this plot into a single number. So what we do is, for every node, we measure the distance of the node to the linear function f of x equals x, which is the red line. We add the squared distances up and divide by n to obtain the average squared error of the embedding. So to present our results, we do this in box plot form. The black bars are essentially the median of all our embeddings. And one such box that represents 75% of all embeddings. And what you can see here is that, two very simple observations. If the average degree delta gets bigger, our embeddings are better. And if the number of nodes get bigger, the squared error decreases, our embeddings are better. This makes sense because if you have more edges or more nodes, we have more information, and then it becomes easier for our algorithm to embed the graph. Now, one other thing I was talking about in the introduction was the successful greedy routing of the internet embedding. So, of course, we asked ourselves, how good is actually greedy routing with our method? And it turns out, if you set t to a small number, let's say smaller than 0.5, as you remember, t adjusts number of long-range edges and short-range non-edges. If the graph is very clean, t is small, then the greedy routing is actually quite good, almost 1. However, if t becomes larger, 0.7 or 0.9, greedy routing quickly deteriorates. And this is actually quite disappointing because for the internet graph, we estimated t to be around 0.7. So we obtained a success ratio of about 75%, whereas the other authors obtained a success ratio of 97%. So at first we were a bit sad because our algorithm clearly performs way worse than theirs. But soon enough, we found actually out if you do the same analysis on generated hyperbolic random graphs, they actually behave almost exactly the same. So if t is 0.7, generated hyperbolic random graphs have only a success ratio of about 75%. So this very good success ratio of the internet embedding was actually much more an artifact of the manual adjustments they made rather than of their algorithm. And the authors themselves were not able to reproduce such a good greedy routing success ratio. And actually, by now, I don't have this in my thesis, but one of our master students actually sat down and wrote an algorithm that optimizes specifically for greedy routing, and there we achieved 100% greedy routing success ratio with just 6% longer paths than optimal paths. So to close, our runtime is of course very good. We can embed thousands of nodes in under a few minutes. And as a proof of concept, we embedded the Amazon product network. So the Amazon product network has 300,000 products, and 2 products have an edge if they're recommended together. Now the nice thing about this network is that it gives you ground truth communities, okay, which are assembled by the product categories. We embedded this graph in under 1 hour, and while we can't plot the whole graph because it's simply too many nodes, you just see black, we can plot the 9 largest communities in this network. And again, what you see here is just basically a rolled out version of the hyperbolic circle. You can see the angular coordinate goes from 0 to 2 pi, and you see the radial coordinate goes from 18 to 24. And what you can immediately see is that most of the product categories are actually mapped very close together, which makes sense, but please remember, our algorithm had no notion of these ground truth communities. It had only as input the original graph. So this is actually quite impressive, and it kind of shows the algorithm does the right thing even for real-world networks. So, to conclude, what have we seen? First of all, in my thesis, we had proved that cliques, and we proved that the largest clique is approximately the same size as in other models if the power law exponent is between 2 and 3. But once it becomes larger than 3, it gives a much more realistic prediction of the clique number for real-world graphs. And also, we have a result that cliques can actually be found very efficiently in hyperbolic random graphs. And for the diameter, we have shown in the thesis that it is actually at least log n. When the power law exponent is between 2 and 3, the diameter is also at most some polylogarithm of n. And for beta larger than 3, we have actually a tight result. And finally, for the embeddings, we have presented an embedding algorithm with quasi-linear runtime, extremely efficient. And we have conducted experiments and saw that we have good results, especially when the number of nodes or the average degree is very high. And having said that, thank you very much for your attention.